Finally, we are now at the end of our theoretical portion for this unit. The climax of this unit were the fundamental theorems of calculus, and we have already given a quote-unquote proof of the second fundamental theorem of calculus. So now in this video, we're gonna give an intuitive, hand-wavy proof of the first fundamental theorem of calculus. To that end, we need to recall the statement of the second fundamental theorem of calculus. Given a nice function v, we can think of it as a velocity function. And in that terminology, the second fundamental theorem of calculus in part 4 said that if we fix any 2 points in time, say 5 and 7, then the sine area under the graph of the velocity function between 5 and 7, that sine area is gonna be equal to the total displacement between 5 and 7, which is by definition just the difference between your position at 7 and your position at 5. Now in part 5, the previous part, we also discussed a more concise way to say the sine area under the graph of v between t equals to 5 and t equals to 7, namely by using definite integral. In that notation then, the second fundamental theorem of calculus says that the definite integral from 5 to 7 of v is going to be equal to the difference s7 minus s5 for any antiderivative s of v. Now, of course, there is no reason why we have to use 7. The same theorem applies if we replace 7 with 6, or if we replace 7 with 9, and so on. So more generally, if we fix a starting time, say 5, then the second fundamental theorem of calculus said that to find the total displacement between our fixed starting point 5 and any other time x, we could just compute the area under the graph of the velocity function lying between 5 and x. As before, this area is denoted by the definite integral from 5 to x of vt dt. Alright, so now here is the idea behind the first fundamental theorem of calculus. Let us denote this area by a of x. Then we can actually view a as a function of x. Observe also that ax is just this definite integral. But usually, when we use this definite integral notation, many people find it psychologically very difficult to think of this as a function of this upper limit x. So instead, for now, we'll denote this by ax. Thus, in particular, this area here, between 5 and 6, that's just a6. This area here is a7, and this area here is a9. To check if you understand, tell me, what is a of 5? Alright, so let's see. So a of 5 would be the area of ax when x move all the way here to 5. But when x move all the way to 5, there is not going to be any area left. So a of 5 is actually going to be 0. Alright, so here we have a function ax. Now this ax is the main star of the first fundamental theorem of calculus. What the first fundamental theorem of calculus claims is that a is actually an antiderivative of v. That is, if we differentiate a with respect to x, then we get v. Do you see why that is? Well, if we cheat and use the second fundamental theorem of calculus, then this is instantaneous. It's obvious. This is because by the second fundamental theorem of calculus, this area is going to be equal to total displacement between the time x and 5, right? So if we take any antiderivative s of v, then we should have that this area is equal to sx minus s5. Now this area is by definition just a, so this means that a is equal to sx minus s5. Now, if you differentiate both sides of this with respect to x, then since s of 5 is constant, its derivative with respect to x is 0, and thus you get that the derivative of a is going to be equal to the derivative of s. But the derivative of s is just v, since s was chosen by definition to be an antiderivative of v. Thus a is also an antiderivative of v, QED. Now, that argument is correct, but it doesn't feel quite satisfying, does it? First of all, it was just symbol manipulation, and second of all, we were, in a sense, cheating because we used the second fundamental theorem of calculus, which usually would come after the first fundamental theorem of calculus. So let us give a more illuminating proof of the fact that the derivative of a is going to be equal to v. It's also a good chance for you to check if you truly understand what derivatives mean. Alright, so let us prove that this area function here is an antiderivative of v. That is, let us show that the derivative of this function with respect to x is gonna be equal to v. Okay, so help me here. Could you please tell me, how do you interpret the derivative of a at x geometrically? What does this quantity tell you geometrically? Here is where many of you will get confused and says that this derivative here should be the slope of the tangent line at x. That mistake comes from the fact that you just vaguely remember that derivatives have something to do with slope of tangent lines. But in mathematics, everything you say or think has to be precise. When you say the derivative of a at x is the slope of the tangent line, you have to specify the tangent line to which graph, at which point. So this is indeed gonna be the slope of some tangent line, but that tangent line is to a different graph. This should be the slope of the tangent line at x to the graph of a, not the graph of v. So remember to be careful there. Now, while this being the slope to the tangent line to the graph of a at x is indeed a geometric interpretation, it's not really what we are looking for, because we are trying to relate a with v, and that description has nothing to do with v, that was only about a. So let us ignore that, and let's try to find a geometric description that relate a with v instead. To this end, we need to remember other ways of thinking about the derivative. Sure, the derivative corresponds to slope of tangent line, but that's just one way of thinking about it. Another way of thinking about the derivative is as the instantaneous rate of change. Think of this region here as expanding through time. At 6 a.m. it looks like this, then at 7 a.m. it looks like this, and at 9 a.m. it looks like this. The derivative of a at a time x then tells you how fast the area is expanding at x a.m. And as mentioned in our video about derivative in this same series, there are two equivalent ways to think about the instantaneous rate of change of a at x. One is via limit and one is via infinitesimal. In terms of limit, recall that we can obtain this instantaneous rate of change by comparing a small change in x with the corresponding change in a. More precisely, when we change x by some small amount delta t, then the area A increased by the area of this thin stripe. And if we take the ratio of the rate of change in A over the rate of change in X, then we get the average rate of change of A over this time interval. And if we now go further and take the limit of this average rate of change as this time interval delta t shrink to 0, then what we get is gonna be the instantaneous rate of change of A at this time x. Now, if you don't want to have to use limit, then recall that an equivalent way of defining this instantaneous rate of change is by letting this time interval delta t be very small. More precisely, we'll let it be an infinitesimal. Then consider the corresponding change in A and actually just take the quotient of that change in A over the change in t. Literally, just the change in a over the change in t. No need for any limit. Note that the picture here is not to scale in that case because you can't technically see an infinitesimal length. That should be the size of a point. Now, both of these viewpoints can be summarized by the following description. The derivative of a at x is just gonna be roughly equal to the ratio of the area of this thin stripe over this interval when this interval is very, very small. But now, observe that when this interval is very, very small, this stripe here will look a lot like a rectangle. And how does one compute the area of a rectangle? Well, one can just multiply the height with the width. Here, the width is delta t. What's the height? Well, observe that the height here is just the y-coordinate of x, right? And what is it? Well, that must be v of x, because this is the graph of v. Thus, the area of this thin stripe is just going to be equal to vx times delta t. So when we divide that by delta t, we should get just vx. Thus, the derivative of a at x is indeed equal to vx. Right? So let us quickly recap that. The derivative of a at x should be approximately equal to the change in a divided by the change in x, when the change in x is small. And geometrically, that's just going to be equal to the quotient of the area of this thin stripe by its width. Now, when the change in x is very small, then this thin stripe is almost a rectangle. So when you divide the area of this thin stripe by its width, you get its height, which is just v of x. And so we have shown that the derivative of a is equal to v, i.e. a is an antiderivative of v. And now if you remember that by definition of definite integral, a is just the definite integral of v from 5 to x, then you can rewrite this statement in the following much scarier way, which is usually the way that you would see it presented. Alright, so that's it for the theoretical aspect of integration. Now all that's remain is the pragmatic computational stuff, which would be much easier. So I'll see you in the next videos.